Welcome to The Explainer. You know, we spend our entire lives swimming in this invisible ocean of sound. It wakes us up in the morning, it makes us dance, it warns us of danger. But have you ever really truly stopped to think about what sound is? Not just as noise, but what's actually happening. Well, today, we're going to break it down.
So let's start with that big question. What is sound, really? It feels so simple, but the answer is this incredible story that connects physics, our own biology, and a whole world that's hiding in plain sight. And believe it or not, the entire thing starts with just one single idea.
And that idea is vibration. That's it. Every single sound you have ever heard in your entire life, from the quietest whisper to a massive sonic boom, it all starts right here.
Okay, so the most important thing to get is that sound isn't just a thing. It's a form of energy, and that energy is always created by something vibrating. If there's no movement, there's no sound, period. That's the #1 rule of the game.
And what do we mean by a vibration? It's literally just the back and forth motion of an object. You know, like a guitar string when you pluck it, or even your own vocal cords when you talk. That super fast wiggle is what kicks off this whole amazing process.
Okay, so the vibration makes the energy. But how does that energy get from the source, like that guitar string, all the way over to your ear? Well, it has to travel, and it travels as a wave. Now, here's a crucial point. Sound is what we call a mechanical wave, and what that means is that it needs stuff to travel through. It needs a medium, like air or water or even a solid object. It absolutely cannot travel through a vacuum. This is the real science behind that classic movie tagline, "In space, no one can hear you scream." Light waves, they can travel through empty space no problem, but sound needs something to carry it.
So how does it actually move through that stuff? The best way to picture it is to think of a long line of dominoes. You push the first one, and it bumps into the next, which bumps into the next, and so on. That forward-pushing energy is a longitudinal wave. The spots where the air particles get all bunched up and create high pressure, we call that compression. And the spots where they spread back out into low pressure, that's called rarefaction. Sound is just an invisible, repeating pattern of these compressions and rarefactions, literally pushing energy through the air to your ear.
And you know, the stuff it's traveling through makes a huge difference in how fast it goes. Sound is actually pretty slow in gases like our air. It's much faster in liquids, and it's fastest of all in solids. Why? Well, it goes back to those dominoes. The particles in a solid are packed together so tightly that they pass that vibration along way more efficiently and way, way faster.
And you've probably experienced this yourself. Think about an approaching train. You can often feel that rumble or even hear it through the solid steel of the track long before you hear the sound of the train coming through the air. That's a perfect real-world example of sound racing through a solid.
All right, so we get what sound is and how it travels. Now let's dig into one of the most interesting things a sound wave can do, which is what happens when it runs into something it can't travel through.
And that, of course, brings us to the echo. An echo is really simple. It's just a sound wave bouncing off a hard surface, like a cliff face or a big building, and coming back to you. It sounds reflection. But have you ever wondered why you only hear a really good echo in certain places? It's not random, it's physics.
To figure this out, we have to solve a little puzzle. And the first piece of our puzzle is the speed of sound itself. In typical air at room temperature, sound zips along at about 344 meters per second. So remember that number. That's our first clue.
Now, the second piece of the puzzle isn't about physics. It's about us. It's about our brains. For your brain to hear a sound and its reflection as two separate things, you know, the sound and then the echo, there has to be a tiny delay between them. That delay is about 1/10 of a second. If it's any shorter than that, our brain just smushes them together, and we perceive it as one single continuous sound.
So let's put it all together. If sound travels 344 meters in a full second, then in that tiny 1/10 of a second gap our brain needs, it travels about 34 meters. But hold on. The sound has to go all the way to the wall and then all the way back. So the wall only needs to be half that distance away. And half of 34 is about 17.2 meters.
It's this perfect little intersection of physics and biology.
So we've covered how a wave moves and bounces around, but how does our brain translate these simple, invisible waves into the incredible richness of what we actually hear, like music and language?
Well, it really boils down to two main characteristics. The first one is called frequency. This is just a measure of how many vibrations or waves happen every single second. We measure it in a unit called hertz, or Hz. And what our brain translates frequency into is what we call pitch.
It's a direct relationship. A high-pitched sound, like a bird chirping or a whistle, is simply a wave with a really high frequency. That means lots and lots of vibrations per second. And a low-pitched sound, like a deep bass drum, has a very low frequency, much fewer vibrations per second. It's that simple.
And the second key characteristic is amplitude. If frequency is how fast the wave is vibrating, amplitude is how big that vibration is. It's the amount of energy or pressure in the wave. And our brain interprets that pressure as loudness or volume. So a really high amplitude wave is a powerful shout, while a low amplitude wave is just a gentle whisper. Now, once we understand these basic principles, frequency and amplitude, this is where it gets really fun. Because we can start to use them to do some truly amazing things, even with sounds that we can't hear at all.
See, the average human ear can only pick up frequencies in a pretty specific range, from about 20 hertz on the low end to 20,000 hertz on the high end. But that's just our little slice of reality. The world of sound is so much bigger. Anything above our hearing range is called ultrasound, and anything below it is called infrasound. The world is literally buzzing with these silent sounds.
And we've figured out how to use them. Sonar is the perfect example. It sounds really complicated, but it's just a high-tech version of an echo. A ship sends out a pulse of high-frequency ultrasound. That sound wave travels through the water, bounces off something like the ocean floor or even a submarine, and that echo travels back to a detector on the ship. And by measuring the time it took for the echo to return, the ship's computer can calculate the exact distance to that object. It's basically just shouting into a canyon and timing the echo, but with technology.
And humans aren't the only ones using these hidden frequencies. The animal kingdom is just full of incredible listeners. Elephants can communicate over huge distances using low-frequency infrasound that we can't feel, let alone hear. And bats, famously, navigate and hunt in total darkness using ultra-high-frequency sounds in a process called echolocation. Their entire world is basically painted with sound.
And that really just leaves us with this one fascinating final thought. From the deep, rumbling infrasound of the Earth itself, to the impossibly high-pitched clicks of a bat navigating the night sky, we are surrounded at all times by an entire universe of sound that our ears are completely deaf to. It really makes you wonder, what other conversations, what other warnings, what other kinds of music are happening all around you right now, just beyond the limits of what you can hear?